Here we have the dot structure for the ethyne molecule, also called the acetylene molecule. And we can see there's a triple bond present now. And each carbon is only bonded to 2 atoms this time. So if we look at this carbon on the left, it's bonded to 2 other atoms. And so I can see that the fact that there's a triple bond here and the fact that it's bonded to 2 other atoms would make me think of a different type of hybridization, right? This can't be sp3 or sp2 hybridization. Let's look at the orbital notation to see if we can figure out the type of hybridization here. So once again, this shows the excited state for the valence electrons of carbon, right? So with the 4 valence electrons, and one of the electrons from the 2s orbital has already been promoted to the 2p orbital. For the example for acetylene, since carbon is bonded to 2 other atoms, we need to form 2 new hybridized orbitals. And we're going to form those hybrid orbitals by promoting the s orbital. So this is the s orbital with its 1 valence electron, and demoting this time only 1 of the p orbitals. So we're going to demote 1 of the p orbitals, right, with its 1 valence electron. That leaves 2 p orbitals untouched. So we're going to leave these 2 p orbitals unhybridized up here. So we're going to take 1 s orbital and 1 p orbital, and we're going to hybridize them together to create 2 sp hybrid orbitals. So this s orbital on the left, what used to be the s orbital, is now an sp hybrid orbital. This p orbital on the right is no longer a p orbital, it is an sp hybrid orbital. Since we formed our new orbitals from 1 s orbital and 1 p orbital, right, this is called sp hybridization. So sp hybridization, like that. And when you see a triple bond present, right, you know that this carbon on one side of the triple bond is sp hybridized, and the carbon over here on the left is also sp hybridized. So we have our new sp hybrid orbitals, which must therefore have 50% s character, right, and 50% p character. So the shape of an sp hybrid orbital is going to look a little bit more like an s orbital than in our previous examples, right? So it's still going to have 2 lobes, a front lobe and a back lobe, just like we saw for sp3 and sp2. The difference is we've increased the amount of s character even more. Now we're up to 50% s character, right? And since s orbitals are spherically shaped and smaller than p orbitals, we can expect these lobes to be a little bit smaller as well. So we can expect this lobe to be a little bit smaller. We're once again going to ignore the back lobe when we do our drawing so that it doesn't confuse us. All right, so 50% S character, 50% P character. If I wanted to draw a picture showing the acetylene molecule and showing it with its sp hybridized orbitals, right? So here's our acetylene molecule. We now know that each carbon is sp hybridized, which means that each carbon is going to have 2 sp hybrid orbitals around it. So these would be the 2 sp hybrid orbitals around it. Each sp hybrid orbital contains 1 valence electron. So let's go ahead and draw that. So we're going to draw the acetylene molecule showing the sp hybrid orbital. So here's one of the carbons on acetylene, and each carbon has 2 sp hybrid orbitals. So here is one of the sp hybrid orbitals. Once again, I'm ignoring the back lobe here, and then here is the other sp hybrid orbital. Each orbital has 1 valence electron, so we go ahead and put our valence electrons in there. For the acetylene molecule, there's another carbon. It also is sp hybridized. So I'm going to go ahead and draw this carbon. It's sp hybridized, meaning there's one sp hybrid orbital. There's another sp hybrid orbital. I'm ignoring the back lobe so it's not confusing. Each sp hybrid orbital has 1 valence electron. So I go ahead and put the 1 valence electron in each. All right, for the acetylene molecule, I have 2 hydrogens. 1 hydrogen is on the carbon on the left, and 1 hydrogen is on the carbon on the right. So I know that hydrogen has 1 valence electron, and that valence electron is in an s orbital. S orbitals are shaped like spheres. So here's the s orbital for the hydrogen atom, and then here is the valence electron for that hydrogen atom. So I go ahead and put in a hydrogen atom over here like that. Let's go back up here to our orbital diagram, right? So we can see that each sp hybridized carbon has 2 unhybridized p orbitals. Each of those unhybridized p orbitals has a valence electron in it. Right? So let's go ahead and draw that down here. This carbon on the left is sp hybridized. Therefore, I know it has 2 unhybridized p orbitals. Each p orbital is shaped like a dumbbell. So here is 1 p orbital, and I know it has 1 valence electron in it like that. And so I need to draw another unhybridized p orbital, right? So here is another unhybridized p orbital, and there is its one valence electron. I do the same thing for the carbon on the right. And so the carbon right is also sp hybridized, which means it has two unhybridized p orbitals. So here is one of the unhybridized p orbitals with its valence electron in it, and then I need one more. So here is the other p orbital, and here is the valence electron. Let's analyze our diagram and figure out what types of bonds we have. So I can see that between my two carbon atoms, there's an overlap of these sp hybrid orbitals, head-on, I should say. So that, of course, is a sigma bond, right? Sigma bond comes from head-on overlap of orbitals. I can see this is also a sigma bond between the sp hybridized orbital of the carbon and the s orbital of the hydrogen. And there's a sigma bond over here as well. So I can immediately see there are 3 sigma bonds in the acetylene molecule. When I look at the p orbitals, right? So these p orbitals here could never overlap head-on, but if they were big enough and they got close enough together in space, you could see there'd be side-by-side overlap of those p orbitals. So we call that a pi bond, right? So there's one pi bond resulting from the side-by-side overlap of those two p orbitals. And if you look over here, there's also an opportunity for these p orbitals to overlap side by side. So there is another pi bond in the molecule. So there are a total of 2 pi bonds. So there are 3 sigma bonds and 2 pi bonds in the molecule. Let's go back to this sigma bond really quickly. So if we look at this sigma bond, the one that's between my 2 carbon atoms, right? This sigma bond is formed from 2 sp hybrid orbitals, which we know are smaller than sp3 or sp2. And that's the reason why you're going to see a triple bond being shorter than a double bond or a single bond. It has to do with the sp hybrid orbital. So if we go ahead and sketch out the dot structure really fast, right, we can see that triple bond there between the carbon atoms. And if we analyze these bonds here, let's just do that really quickly. So if I look at the dot structure and I'm trying to figure out how many sigma or pi bonds I have, all I have to do is count up the single bonds, and that'll tell me how many sigma bonds I have. So here's a single bond, so that's a sigma bond. Here's a single bond, so that's a sigma bond. And here I have the triple bond between my carbons. I know that one of those bonds is a sigma bond. It doesn't really matter which one you say it is for the dot structure, so I'm just going to say it's this one. Right? So that gives me my 3 sigma bonds. When I'm trying to figure out pi bonds, I know in a triple bond there's 1 sigma bond and 2 pi bonds. So these must represent my pi bonds, and so those are my 2 pi bonds like that. And so once again, for a triple bond, right, this is going to be the shortest bond length due to the fact that the sigma bond comes from the overlap, the head-on overlap of 2 sp hybrid orbitals. When I think about bond angles, right, when I think about the angle between this hydrogen, this carbon, and this carbon here, I can see that it's going to be, right, this is a straight line over here in my diagram. So let me see if I can draw this really fast, right? So this is a straight line running through all of these atoms right here. So therefore, the bond angle must be 180 degrees, right? So I have 180 degrees here. And you can see that that straight line runs through all of my sp hybrid orbitals. So it's those hybrid orbitals that are going to determine the geometry. The pi bonds will help to stabilize that and prevent any free rotation, right? So the pi bonds are going to make sure that the triple bond cannot undergo any kind of free rotation. Let's do one example to sum up everything we've learned about sp3 hybridization, sp2, and sp. So if I start with just a drawing of a molecule here, so let's go ahead and put in some carbons, right, and some hydrogens like that. So here we have our molecule, and let's try to answer a few questions about this molecule. The first question would be to identify the hybridization state of each carbon. Right? So if I look at this carbon, right, I can see that there's a double bond present. So I can immediately say it's sp2 hybridized. Same thing for this carbon, right? It also has a double bond, so it's sp2 hybridized. This carbon over here, right, this one has only single bonds around it. So we saw in the video in sp3 hybridization that this carbon must be sp3 hybridized. And we've just seen in this video how if you have a triple bond present, right, those carbons must be sp hybridized. All right, next let's think about the shape and also the bond angle, right? So if we think about first, let's start with the sp3 hybridized carbon. We saw in the sp3 in the video on sp3 hybridization that the atoms around it want to try to adopt a tetrahedral bond angle and try to get as close as possible to 109.5 degrees. So that takes care of sp3 hybridization. sp2 hybridization, right? We saw that that's going to give us a trigonal planar geometry for the atoms around those carbons with a bond angle of approximately 120 degrees. For sp hybridization, we saw in this video, right, that's going to be linear, which is why I've drawn the dot structure as being linear, and giving us a bond angle of 180 degrees. Finally, let's count up the number of sigma and pi bonds in this molecule. So I'm going to start with the number of sigma bonds. So all I have to do is count up my single bonds. So this is 1, 2, 3. For a double bond, I know one of those is a sigma bond for my video on sp2 hybridization. So 4, 5, 6, 7, 8, 9. And then in this video, we saw that for a triple bond, one of those is a sigma bond, right? So one of those is a sigma bond there. So there's a total of 10 sigma bonds. So we just counted 10 sigma bonds. What about pi bonds? Well, those would be the ones that are left, right? So in a double bond, you have one sigma bond and one pi bond. So this should be a pi bond. For a triple bond, we have one sigma bond and two pi bonds. So there are a total of 3 pi bonds for this molecule. So this is the type of question that you are usually asked in a test for organic chemistry, and you should be able to analyze organic molecules this way. It's an important skill for later in the course.